Hey, in this one I wanted to show you a thing that I think a lot of people encounter, but I'm not sure, I wasn't sure how to explain it when I first encountered it before I understood L values and R values. And I already have a video about that you can watch, but let's say you don't really have to understand L values and R values to understand this example. So here I have a string, and I'm passing it to the function foo as a reference. And so then it prints its size. And you will notice that oftentimes in your code, if your function takes a string and you try to, if it takes a string reference and you try to do this, you get an error. But if you make it const, it compiles just fine. And this is like a different string, so size can be 6. And so what is the difference? What kind of tricks did the compiler pull that if it's not const, it doesn't work, but if it is const, it works. That's just kind of interesting to me. And so yeah, let's make it clearer by calling std string directly, because that gets rid of something else that gets in the way. But let's say yeah. So this, if you call std string like this is an R value, which is kind of a temporary value. And so a temporary value has to be stored somewhere. And so here, if you only take a reference, let's say I would take a reference, and then here I'm just getting the size. So you might think it's okay, but what if I want to modify the string and like say I don't know, by like this. What if I wanted to add something to the string? Then you would need to add something to a temporary value, which is a bit strange. Like, how does that even work? And so this is why it needs to be const if you have a temporary value, to passing a temporary value as an argument, because then if it's const, well, you just cannot modify it, so that gets rid of this problem, and then the compiler is sure that it can do like the little trick that I was talking about, which is basically it will allocate it on the stack for you. So under the hood, it will do this and replace it by s, like so. So yeah, this is a slightly confusing, but basically it can only do this trick if it knows that the thing has a place somewhere in memory. So yeah, and we can see this on Compiler Explorer. So I have the same example here. Like if I have a little main with a function foo that takes a const reference to string, and then I return its size. And here I pass in a temporary string. And so we can see that, well, it's a bit hard to read with the string constructor template thing being so complicated, but yeah, here I call size. And so where I call foo is, where do I call foo? Foo is called here, okay? And it's called with whatever is in RDI, and we can see that RDI is initiated with RBP minus 80, and RBP is basically the stack pointer. And so when you see RBP minus something, it means the offset at which this value is on the stack. So you can see that even yeah, you can see that the compiler has allocated some memory on the stack for me, because I haven't done it. And it has called the string constructor here, again with RBP minus 80, which is somewhere on the stack. So yeah, it's just a kind of a cool trick that the compiler can pull off. I mean, I don't know, it's kind of nice when you know about it, but for the first few times when you encountered it, it's extremely confusing, like a lot of things in C++. And yeah, that's also kind of a good argument as to why you should make every single one of your references const if possible. I mean, obviously, it just makes the program a lot clearer to to the user of your function that okay, this is a reference or a pointer, and it will not be modified. But also, the compiler can have some tricks if you add const. So yeah, it's kind of nice. So yeah, that's all I've got. See you.